Okay, let's start for the meeting. So we have a series of talks on literature and history of mathematical science organized by CMSA in Harvard University and jointly with Tsinghua University, the Math YMSC. This will be the third lecture in the next couple of weeks. So I will ask Bawa to chair this session. Bawa.
Okay, so today we have Professor Caucher Birkar to speak. He is one of the leading experts in algebraic geometry. He has made several fundamental contributions to birational geometry, especially for the existence of flips and for the proof of BAB conjecture. His work has led major advances in birational geometry and has changed the landscape of research in higher dimensional geometry. So we are very happy to have him to speak here. And today, his talk title is Log Calabi-Yau fibrations. Okay, please.
Thank you very much, Professor Yao and Bahua. I will talk about Calabials today, but in a more general setting, which I will explain when I go through the talk. So let me first fix a few notation and the setup. We will work over the complex numbers, although this is not really necessary. For many of the statements, we can take any algebraically closed field of characteristic 0. And in fact, many statements, at least conjecturally, make sense or in positive characteristicals. But for simplicity, let's just work over the complex numbers. The usual n-dimensional affine space will be denoted by the standard notation AN. Pn will be then the n-dimensional projective space. This is a compactification of AN. And we will work with quasi-projective varieties sitting inside projective spaces. In many cases, we will just take projective varieties. Now, algebraic geometry is largely, to almost, maybe you could even take it as a definition, as being the classification theory of this type of varieties. So there are more general type of varieties which are not necessarily quasi-projective, but almost all the fundamental problems in algebraic geometry have to do with just quasi-projective varieties. Now, it turns out that in this classification scheme, that there are some special algebraic varieties, for example, Fano varieties and Calabi-Yau varieties, and their more general forms, and they play a fundamental role in this classification theory. In fact, this goes well beyond algebraic geometry, also in differential geometry, up to some extent in arithmetic geometry and so on. These type of special varieties are just happen to be fundamental. But in algebraic geometry, we can see this very clearly why this is the case. Now, this kind of varieties, Fano varieties and Calabi-Yau varieties, they fit into a more general framework, which I call log Calabi-Yau fibrations. These are basically spaces X together with a boundary divisor. So that's why we call them log. Log just means this presence of this extra structure, which is the divisor. And the fibration just emphasizes the fact that this is a structure relatively defined over a base. It's not necessarily a global, not necessarily projective, but relatively projective. In fact, fibration here is a bit of abuse of language, because this is not really a fibration, basically just a morphism with connected fibers. In particular, it can be birational, it can also be even identity. Even in that case, this can tell something very interesting and non-trivial. I will go into these details during the talk. Now, this general framework of local Avial fibrations, it covers an incredible range of notions, concepts, and also known results and open problems. So there are probably, I don't know, hundreds of open problems related to this kind of structure. During the talk, I will mention some of these open problems. And now it's basically impossible to state all the known results in this direction because it has a very, very long history, even going back to the ancient times. So what I will do will be just selective. Select some results, which then naturally will be a bit biased in the sense that I will select the thing that I am more interested in. Especially, I will mention some of my own results also. Okay, so let's see what this is all about. Let's start with Fano varieties. Fano variety is a projective variety X with good singularities. At the moment, I don't tell you exactly what good singularities means, but you can just assume to be smooth if you like. Later, I will define singularities. So we have a projective variety X with some reasonable singularities and minus the canonical divisor or the dual of the canonical bundle is ample. So minus K is ample. Now, I can go through a long list of examples. The most fundamental example of a Fano variety is just the projective space. Now, this kind of space, as I mentioned before, is a compactification of the usual n-dimensional space. So the usual n-dimensional space, you can just think of it as being the complex numbers product with itself n times. And then if you compactify that, if you add something at the infinity, then you get the projective space. This kind of compactification was inspired by projective geometry. Now, although Pn itself, in a sense, is a very simple kind of Fano variety, I mean, if you just look at it as a single algebraic variety, but in fact, it's not as simple as it looks. For example, if you study its relation with other varieties, for example, its relations with itself, if you look at all the meromorphic functions from Pn to itself, then you get something very complicated. But in a way, we can think about it as something simple, maybe the simplest Fano variety. Now, hypersurfaces inside this projective space of degree at most, the dimension of the projective space, will naturally give you Fano varieties. Just for simple reasons, you just apply the so-called adjunction formula to calculate the canonical divisor of X, and you see that the fact that the degree of this hypersurface, the degree here is just the degree of the polynomial which defines X, is bounded by n, then it becomes a Fano because the canonical bundle, the canonical divisor of Pn is minus n plus 1 times a hyperplane. And that's the reason this becomes Fano. So this gives you a lot of examples. For instance, if you take n to be 2, then all the degree 1 and degree 2 equations, if the hypersurface, let's say, is smooth or some nice singularities, then it will give you Fanos. Although this type of singularity that I will talk about later, there will be, I mean, we force X to be a normal variety. So in this case, normal will be just smooth in the two-dimensional projective space case. Now, you can also intersect hypersurfaces inside this projective space to get a lot more examples. For instance, if we go inside P3, take a hypersurface of degree 2 and take a hypersurface of degree 1 and intersect them, assuming that the intersection is nice enough, then we get a so-called conic section, and this conic section becomes naturally will be a Fano variety for the similar reasons, because you can apply adjunction twice and then you get something which is Fano. So in this particular case, this H will be just P2. And the intersection of C with H will be something defined by a degree 2 equation. So it will be a conic. In fact, this kind of construction goes back to the ancient times. It goes back to Apollonius, who looked at a cone and then intersected with planes and looked. So he saw that these intersections are in a way special, and they are conic sections. So if you take this C, for example, to be a cone, you basically get similar picture. Much more generally, if you take Pn and then intersect hypersurfaces again, assuming that the sum of the degrees will be at most n, then you get again Fano varieties. This here need to be complete intersections and singularities. Suppose they are nice, then you get a lot of examples of Fano varieties. Now, a much more general kind of construction is if you take any toric, projective toric variety, let's say W, and if you look at this minus canonical divisor, this is not usually ample, so it may not be a Fano variety, but we can make it ample. There is a process, this is related to the minimal model program, which I will talk about later, and it produces a new toric variety X, where this minus K is actually ample, and it gives you a new toric variety, which is a Fano variety. So this process, this recipe gives you a lot of examples, of interesting examples of Fano varieties. So one of these particular examples are weighted projective spaces. They are denoted by P A0 to AN, where these numbers, these are non-negative, these are positive integers. So if you take all of them to be 1, you just get Pn, but otherwise you can get new spaces. But they are Fano varieties. And you can also take complete intersections inside these weighted projective spaces with appropriate degrees, similar to this condition here. And under some other assumptions, then you get again Fano varieties. Finally, Grassmannians also give you another example of Fano varieties. So there are a lot of examples of Fanos if you haven't seen these things before. But now we are more interested in the general properties of Fano varieties. Now, in dimension 1, P1 is the only Fano variety. And that is not difficult to see if you just look at the genus. For example, the genus has to be equal to 0 if minus K is ample. In dimension 2, there are a lot more surfaces, Fano surfaces, and these are called Del Peso surfaces. And there is a classification of this kind of surfaces, at least in the smooth case. But if you add the singular one, then you get a lot more Fano varieties in dimension 2. But they are basically well known because we know so much about surfaces in general. Now, in dimension 3, Fano, that's where the name Fano comes from, he studied Fano varieties of dimension 3. And this study, which happened in the early 20th century, it was a very crucial kind of research because it helped to extend this classification theory, in particular birational geometry, to higher dimensions, to dimension 2. So the two-dimensional case was already, you could say, well understood by late 19th century, early 20th century, but it took a lot longer time to understand even the first steps of the three-dimensional case. But Fano was one of those people who started this kind of studies. And the reason he focused on Fanos is simply because they look to be more accessible. Now, much later in the early 70s, Iskowski and Manning, they developed techniques of Noether and Fano and Segre. They started basically this work of Fano, and Fano himself used ideas of Noether and so on. And then Iskowski and Manning, they show that there is a counterexample to the Luros problem. The Luros problem asks whether a unirational variety is always rational or not, but they show that this is not the case. And the way they did it was that they looked at threefold quartics. So these are hypersurfaces in the four-dimensional space defined by polynomials of degree 4. And they show that these are not rational. In fact, they showed something much stronger. They showed that these are rigid. I will come back to this point later. So this also, in a way, you could say this was the second push to extend this classification to the three-dimensional case. There were also other works, especially by Itaka in a different flavor. But this particular result was very important. And later it led to a lot more results in this direction for showing rigidity and non-rationality of Fano varieties. And a few years later, Shakurov showed that if you take any smooth Fano threefold, and if you look at the global sections of minus k, the divisors defined by these global sections give you a so-called linear system. And he showed that on every smooth Fano threefold, in this anti-canonical system, you can find a smooth element. And this was quite important. One reason is because it helped a classification effort of Iskovsky and Mori and Mukai to be completed. And another importance of this result was that it was essentially the origins of Shakurov's theory of complements, which has been very, very important in more recent years. Again, I will come back to this later in the talk. Now, a few years later, not so, maybe in the late 70s, Mori proved the so-called Hartshorne conjecture. He proved that the projective spaces are the only smooth projective varieties with ample tangent bundle. And of course, this was an important conjecture on its own, but its solution was even much more important than the conjecture. In the process of solving this conjecture, Mori introduced the so-called bend and break technique. And also this led to the theory of extremal rays. So Mori's idea was that you take a curve inside your variety and you use the fact that the tangent bundle is ample, you deform this curve, or to be more precise, the morphism given by the inclusion of this curve into the variety, and then you produce rational curves going through every point of this variety. And this is the so-called bend and break technique, and it happened to be extremely important because it also works when under much more general conditions. When you take a smooth projective variety where the canonical bundle is not Neff. In other words, if there is even one curve which intersects the canonical bundle negatively, you can produce some rational curve. And that plays a very important role. It basically led to the birth of Mori theory, or the minimal model program in dimension 3. This was, of course, also in conjunction with work of many other people, notably Kawamata, Reed, Shakurov, Kolar, Miyaoka, and so on. So there are many people in the 70s and in the 80s who tried to extend this birational geometry to dimension 3. And so Mori's work produced one of the main inputs, but there were also other works, like especially Kawamata and Shakurov, who used cohomology theory to prove some of the parts of some of the ingredients of this minimal model program. Again, I will come back to the minimal model program later. So you see that this was, it was something about Fanos. I mean, these last few things we have mentioned here, they are all about Fano varieties, but it did naturally lead to results about other varieties which are not Fanos. For example, varieties of general type, or just any arbitrary smooth projective threefold. These techniques say something about those varieties also. So the point is that if you say something about Fanos, in many cases, you may be led to something about more general situations. So they are, from a historical point of view, they're extremely important because they have led to other developments. Now, at about the same time, Siu and Yau proved the so-called Tranquil Conjecture, which is a differential geometric version of Hartshorne conjecture. And the result basically say that if you have a compact scalar manifold of positive holomorphic bisectional curvature, then this should be biholomorphic to some projective space. In the Morris case, his condition was that the tangent bundle is ample, but here we have a differential geometric condition, and this also implies that you have only one choice, which is in each dimension, which is just Pn. So the techniques here were quite different from Morris' techniques. They use different ideas. But let me go back to algebraic geometry. Now, so this, what I said was in the 70s and early 80s, but later in the 90s, Shakurov introduced formally the theory of complements. So what he says that if you take a Fano variety X, then he studied nice elements in not only in the anti-canonical system, but in multiples of the anti-canonical system. So he looked at these things even in a relative situation, not just globally, but you could have even just one single point and you can still talk about this kind of objects. So he basically more or less completed this thing in dimension 2, and then later also developed with Prokhorov. In much more recently, a few years ago, I approved one of the main conjectures in this direction, which says that you can always find nice elements in these pluricanonical, pluri-anticanonical systems for n which depends only on the dimension. So this X here is not necessarily smooth. It has, in fact, so-called KLT singularities. But you can always find something which depends only on the dimension, but not on the type of the singularity. So this is a really remarkable conjecture, which says, for example, if you take just a singularity of that type, let's say KLT, then it tells you basically that you can always find a nice divisor. You add this divisor to the canonical bundle, and then the torsion index of this, the sum of the canonical divisor plus this new divisor is bounded by some number n. So that says something about the singularities. And at about more or less the same time, I also proved the so-called Borisov conjecture, which says that if you bound the type of singularities on Fano varieties of a fixed dimension, then they form a bounded family. So there are many special cases of this proved in the literature, especially Alexia proved it in dimension 2, and the Borisov brothers, they proved it for the Toric case, and that's how they came up with the conjecture. But there were other cases like the smooth case, which was known. In dimension 3, the smooth case, in fact, even I think Fano already tried to prove this thing, but not a complete proof. Now, there are more developments a bit here, again, related to differential geometry. Chen, Danielson, and Sun, they proved the so-called Yao-Tian-Danielson conjecture, which says that a smooth Fano variety X admits a Kähler-Einstein metric if and only if X is K stable in some sense. Now, on one side, you have a differential geometry, you have existence of some kind of metric. This is not an algebraic statement, but on the other side, you have something that is purely formulated in terms of algebraic geometry. So it is also another important development. There are also work of Tian related to this. This is not so long ago, just maybe less than 10 years ago. And on the other hand, Shramov and Prokhorov, they studied birational automorphism groups of Fano varieties X, and even more generally, rationally connected varieties. And they assumed the boundedness result that I mentioned a bit ago, this Alexei Borisov conjecture. They say that if you have that, then this kind of birational automorphism groups satisfy a property which is called Jordan property. It essentially says that if you take any finite subgroup of this group, then you can always find a normal abelian subgroup with bounded index. So this was also really nice, because these kind of groups are quite complicated. Even when you take X to be the projective space, these groups are very hard to understand. In fact, much more recently, Blanc, Lamy, and Zimmerman, they showed that the birational automorphism group of Pn is not simple for n more than or equal to 3. This was already known for the case n equal to 2 by Cantat and Lamy. So again, this is also a difficult result. It relies on all these boundedness results and so on. So you see already in the Fano case, we have a lot of results, but I will also mention conjectures later. Now, so far, I have only talked about the global situation, meaning that I have a projective Fano variety. But what happens if we take the relative situation, when we have something, a Fano vibration? So a Fano vibration is a vibration here. It may not be a positive dimensional vibration, but just basically a morphism with connected fibers, which is relatively projective. So X and Z, they don't have to be projective. Again, we assume that X has good singularities and that minus K is ample relatively over Z. So even the case when X to Z is the identity, this is allowed. Let me just mention some examples. If you take X to be usual global Fano and Z to be a point, then this is one of those examples. If you take X to Z to be a Pn bundle, then again you get a relative Fano, a Fano vibration. Much more generally, if you take a Mori fiber space, then you get a Fano vibration. But even birational case can give you a Fano vibration. For example, a flipping contraction, which is an important ingredient of the minimal model program, this is also considered as this relative Fano or Fano vibration. Or divisorial contractions, when you contract devices. This is similar to contracting -1 curves on surfaces. And even the case when X to Z is just the identity, then this becomes basically singularity theory. It's about understanding the singularities near a germ, near a point. So there are a lot of interesting examples, but so in general, when you are given a Fano vibration, you want to understand what happens, what is the geometry here involved, especially how can you relate the geometry of X to the geometry of the base Z and to the fibers of this vibration. So let me take one of these examples, the case of flipping contractions. By definition, basically, this is a birational Fano morphism. Birational, so the fibers will be mostly just points, but you are allowed to contract some positive dimensional subvarieties, but not devices. But you need to contract something at least. So they are important in a minimal model program. And when you have one of these flipping contractions, then you say that the flip of this contraction, this vibration exists. In fact, I mean, there is a definition for what it means for the flip to exist, but it's equivalent to this quite algebraic condition, which says that if you take all the multiples of the canonical divisor of X, and if you take their sheaves and push them down on Z, and you take the direct sum of all these things, then you get an algebra. This is an algebra over the structure sheaf of Z. So to have a flip is equivalent to saying that this is a finitely generated algebra. So this is a very non-trivial problem. And Mori proved this existence of flips in dimension 3 for so-called terminal singularities. This is one of the highlights of Mori's work. And Shakurov proved this in a more general setting in dimension 3, but also proved it in dimension 4, and also gave ideas of what to do in higher dimension. Then Heiken and McKernan, they fused these ideas of Shakurov with ideas coming from other places, especially multiplier ideal sheaves. And they showed what to do inductively to prove flips. And finally, the whole thing was settled in the so-called BCHM paper. So we now know that flips exist in every dimension. So I discussed this because I just wanted to tell you that when you go out of the global situation, you can still end up with very non-trivial problems or facts. Okay, that's maybe enough about Fano varieties. Let's talk about Calabi-Yau varieties now. A Calabi-Yau variety is a projective variety X with good singularity such that the canonical divisor is trivial. So in the Fano case, we had minus k was ample, but here k or minus k is trivial from a numerical point of view. It means that intersection with any curve is 0. Again, there are examples, a lot of examples of Calabi-Yaus. In dimension 1, these are exactly elliptic curves. We can produce Calabi-Yaus using hypersurfaces similar to the Fano case, but this time we need to take hypersurfaces in Pn of degree exactly n+1. When you apply a junction, you see that you get indeed Calabi-Yau. Now in dimension 2, there are examples like K3 surfaces, abelian surfaces, Enriquez surfaces, Kummer surfaces, and so on. In general, in any dimension, we have abelian varieties. They are all Calabi-Yau. Now we can produce complete intersections inside Pn when the sum of the degrees is exactly n+1. Again, we get Calabi-Yaus. We can also look at complete intersections similarly in weighted projective spaces. And another way of producing Calabi-Yaus is to look at a Fano variety Y, let's say smooth Fano variety, such that in the anti-canonical system of this Fano, we have some smooth elements. In that case, then X automatically will be Calabi-Yau. You just apply a junction and you see that this is in fact a Calabi-Yau variety. So there are a lot of examples of Calabi-Yau varieties. Now, one of the most important facts about Calabi-Yau, and that's where the name comes from, is the fact that Yau proved the so-called Calabi conjecture, which a special form of it says that on any smooth Calabi-Yau variety, there is a Kähler metric with vanishing Ricci curvature. Of course, this is a consequence of the more general theorem of Yau. That's why they are called Calabi-Yau varieties. Now, in the context of Calabi-Yau varieties, mirror symmetry, very roughly speaking, says that smooth Calabi-Yau varieties come in pairs. They are mirror to each other in some sense. Hopefully, I will come back to this point also at the end of the talk. Now, mirror symmetry is a fundamental tool in string theory, but also in algebraic geometry. This is related to enumerative geometry. So this means, for example, you want to count the number of curves in some Calabi-Yau varieties with some conditions. And mirror symmetry is directly related to this kind of problems. In a very different direction, let me mention this conjecture, which says that if X is a smooth Calabi-Yau variety, in fact, even with singularities, but with appropriate conditions here, and if L is a Neff divisor, Neff means that intersection of the divisor with any curve is non-negative. Then this divisor is numerically equivalent to some other divisor, such that this other divisor M is semi-ample. And semi-ample here means that some multiple of this divisor is generated by global sections. So here we might have to take divisors with rational coefficients. This is the so-called semi-ampleness conjecture on Calabi-Yau varieties. Is a very difficult problem. It's opened already in dimension 3. But it says something fundamental, that if you have any Calabi-Yau and if you have a Neff divisor, then this Neff divisor, in fact, is at least numerically semi-ample. And in particular, that implies that this divisor defines a morphism. So if it is ample, then that's nothing happened. But if it is not ample, that means that you actually have a morphism from X to some other variety, and you are contracting something. That's a very non-trivial fact, and it's a very hard conjecture. Now, similar to the Fano case, we have also a relative Calabi-Yaus, or in other words, Calabi-Yau fibrations. And again, fibration here may not be with positive fibers. So basically, there's any morphism projective and with connected fibers such that Kx is relatively trivial over Z. So globally, it may not be trivial, and it may not, X itself or X and Z, they may not even be projective. So globally, it is may not be very interesting to say whether K is trivial or not, but relatively, we have this projectivity and this triviality. So we get Calabi-Yaus. And some of the examples of these relative Calabi-Yaus are when X is a usual Calabi-Yau variety and Z is just a point. So we just get global Calabi-Yaus. Another trivial example is if you take F to be a Calabi-Yau variety and X to be the product of F with some other variety, and then you take the projection, and that gives you a Calabi-Yau fibration. And another less trivial example is elliptic varieties. One special case is elliptic surfaces. So there are many surfaces X which come with an elliptic fibration. And that means that we have a fibration from the surface onto a curve, and most of the fibers are elliptic curves, but maybe some of them are singular. So that's quite important in the classification theory of surfaces. Now also, if you have a variety Z and take the product with some projective space Pn, and then you can take relative hypersurfaces that relatively they have degree n+1, then you get relative Calabi-Yaus. So there are a lot of examples of relative Calabi-Yaus, but when you go to the locus situation, you find a lot more examples. Now let me mention some results and problems in this direction. Suppose that we have a Calabi-Yau fibration from X to Z, then consider all other Calabi-Yau fibrations over the same Z, but such that the total spaces are isomorphic in codimension 1. So they may not be isomorphic, but they are isomorphic outside some codimension more than or equal to 2 subset. Then one result that we know in this direction is the result of Kawamata, which says that this kind of varieties X and X prime, they can be connected together by a sequence, by a finite sequence of flops. Flops are similar to flips. So for example, if you just take Z to be a point, this is saying that if you take any two Calabi-Yau varieties which are isomorphic in codimension 1, then they are always connected by some kind of more elementary kind of birational maps, which are called flops. And there is a very hard conjecture of Morrison and Kawamata, which says that up to isomorphism, if you are, so we have X to Z, which is fixed, then the conjecture says that up to isomorphism, there are only finitely many other Calabi-Yaus over Z, which is birational, which is isomorphic in codimension with a given X. So for example, again, if you take Z to be a point, it's saying that if you fix a Calabi-Yau and look at all the other Calabi-Yaus, which are isomorphic in codimension 1 with this given X, then in fact, up to birational, I mean, the birational maps themselves, they may not be finite. You may have infinitely many, but up to isomorphism as abstract varieties, you have only finitely many Calabi-Yaus, and this is quite difficult. Okay, so now that I have defined Fanos and Calabi-Yaus and given you some examples and some results and some problems, I mentioned a couple of times that this minimal model program. Let me just say a few words about this. Very roughly speaking, suppose that we have, let's say we start with a smooth projective variety W. Now, the aim of the minimal model program is to transform this variety W in very precise step-by-step program, and you end up in the end, if everything works, you end up with something which is much simpler than the original variety because it satisfies some extreme conditions. To be a little bit more precise, if we have W, then there are operations. Some of them are called divisorial contractions and some are called flips. You can take a combination of this kind of operations, these transformations. These are all birational transformations, such that the program is designed in a way that in every step you try to make the canonical bundle more positive by trying to get rid of the places, the curves where the canonical bundle is negative. And in the end, in fact, every step here is basically a Fano fibration. So this Morris program, this minimal model program, is essentially looking at directions where you have a Fano fibration. Now, this whole program is complete up to dimension 3. We also know many things in every dimension, but it's still wide open. So let me just summarize what we don't know. One of the very hard problems is that we don't know whether this program stops after finitely many steps or not. This is called the termination conjecture. So potentially you could have infinitely many flips. We don't know why there should be only finitely many. We know up to dimension 3, but even in dimension 4, we don't know in full generality why there should be only finitely many. At least when you have the general case of singularities. Now, another even harder problem is that is the so-called abundance conjecture, which roughly speaking says that suppose that we already know the termination, that we end up with something. So we end up with a place where this program doesn't give you anything new. There is nothing negative to be contracted. And then the abundance says that, well, in that case, you either have a Fano fibration, which is a fibration in a genuine sense, in the sense that the fibers are actually positive dimensional, or if this doesn't happen, this X should have a Calabi-Yau fibration. Now, in this case, also the fibers will be again genuine. Fibration will be genuine in the sense that fibers will be positive dimensional. So you have either a non-trivial Fano fibration or non-trivial Calabi-Yau fibration, or if these two don't happen, then the canonical bundle is almost ample. It's very close to being ample. To be more precise, it will be Neff and big. So this is one of the main reasons why Fanos and Calabials are so important in algebraic geometry, because this program says that if everything works as expected, it says that if you start with any smooth projective variety or even projective variety with reasonable singularities like KLT or low canonical, then after a finite number of steps, where the steps themselves are quite interesting, in the end you get a Fano fibration, a Calabi-Yau fibration, or something which is almost as positive, as nice as you could hope for. So that shows the importance of Fanos and Calabi-Yaus, but also the importance of the program is that if you understand X, then in theory you can go back step by step and understand W, understand the original variety. So this is not really a birational classification, as many people usually say, birational geometry. This is not really birational geometry. This is just biregular geometry, because we try to understand everything in the whole process. It's not just about understanding X, but also the original variety W. But what is important about X is that it satisfies these very nice properties. So it's much easier to discover something about X rather than about a typical arbitrary variety W. Okay. Now I have mentioned singularities quite a few times, but let me now give you a formal definition. So if you have never seen this before, it may look quite strange, but experience shows that this is very natural. Now we define singularities not just for one variety, but for a pair. A pair XB, this means we have a normal variety X together with a boundary divisor B, where the coefficients of these B are between 0 and 1. So they can be rational numbers, they can even be real numbers. So the simplest example would be if you take X to be smooth, for example, smooth projective variety or just smooth variety, and B to be something with simple normal crossing. That's the simplest kind of pair. Now, in general, when you are given a pair, the singularities of this pair are defined by taking a resolution of the singularities and comparing your pair with what you have on the resolution. More precisely, by Hironaka, there is a log resolution, let's say W to X. We take the pullback of K plus B, and here, to be able to do this pullback, we need to assume that, for example, this is a Cartier up to some multiple. But we don't need to worry about that now. And then we can write down the pullback of K plus B as K of W plus some divisor, which is uniquely determined by the pair. And just by looking at the coefficients of this divisor or the resolution, we can define what type of singularities we have. For example, we say that the pair is epsilon log canonical if every coefficient of BW is less than or equal to 1 minus epsilon. So roughly speaking, the larger the coefficients of BW, the worse the singularities on XB. Conversely, the smaller the coefficients in BW, so they can be also negative, the better, the nicer the singularities of XB are. But counterintuitively, in algebraic geometry, in fact, we make use a lot of the fact that sometimes we have pairs with bad singularities. So bad singularities is actually, in practice, doesn't always mean bad. Quite often, it means you can do something with these bad singularities. So it of course depends on the context. Now, log canonical just means 0 log canonical, and KLT means epsilon log canonical for some positive epsilon. So if you have never seen this thing before, you can just think about this as a way of measuring singularities of a space together with a divisor. In fact, you could take even not just divisor, you could take also subvarieties of higher codimension. Now, some examples of this is, as I said before, if you take X to be a smooth variety and B to be a simple normal crossing divisor, for example, X take it to be P2 and B to be a bunch of curves that they intersect nicely and the curves themselves are smooth, then you get something which is log canonical. But if you assign coefficients less than 1 here, you get KLT. Another example of log canonical is when you take X to be a smooth surface like P2 and B to be a nodal curve, a curve with a nodal singularity, something that intersects itself but in a nice way. This becomes log canonical, but if you take a cuspidal singularity, then this is not log canonical anymore. Another thing which is log canonical but not KLT is if you take X to be a cone over an elliptic curve, then you get log canonical, not KLT. And if you take cones over rational curves of, let's say, degree n, you get KLT, but the type of the singularity will depend on what kind of degree you have for the curve. So you can take a look at quotient singularities and so on. There are a lot of examples of singularities, but just hopefully just give you a flavor of what we look at. Now, so I come to the point where I can define a log Calabi-Yau fibration. This is more general than what we have seen so far. A log Calabi-Yau fibration then is a pair XB together with a morphism, which is just a projective morphism with connected fibers. So it can be birational, for example, or it can be genuine fibration. We assume that the singularities of this pair are nice, like low canonical or KLT. And also we assume that K plus B is relatively trivial in a numerical sense over the base. So globally, you may not have triviality, but locally you have, relatively you have something trivial. So let's look at some examples. All the Calabi-Yau varieties and all their fibrations are naturally low Calabi-Yau fibrations. All Fano varieties and Fano fibrations, let's say X to Z, they can be naturally considered as low Calabi-Yau because you can just take some B, some divisor B in the anti-canonical system relatively over Z. This is not a unique choice. So you can have like infinitely many choices, but you just can turn any Fano into a low Calabi-Yau. Another example is of toric vibrations. So if you have any toric pair, if X is toric and if B, the divisor, is a toric divisor, and if you have a toric morphism to some other Z, so this is naturally K plus B will be just automatically trivial, and therefore it gives you a low Calabi-Yau vibration. In general, if you run this minimal model program on any low canonical pair, let's say W and C, this in the end, it will give you a low Calabi-Yau vibration, just as we saw in the abundance conjecture. Now, in the case when you take XB to be a low canonical pair and X to be the same as Z, so X to Z is just the identity, then here you are looking at singularities of pairs near some point. So you see that this covers a lot of different type of morphisms and pairs. Now, there are many general questions about low Calabi-Yau fibrations that one can ask. For example, you can ask under what kind of conditions this type of fibrations are bounded. Bounded means that they form a bounded family in the sense of algebraic geometry. So we already saw some examples. When X was, for example, a smooth Fano variety of fixed dimension, then these are bounded, even with some type of singularities. And you can also ask how the linear systems minus NK behave relatively over Z. This is related to complement theory. But in general, they can be very hard to understand, as I will mention some problems. And then you can ask about singularities. How the singularities on X and Z behave? How are they related? If you know something about X, can you say something about Z? And the other way around. If you know something about Z, does that say something about X? Another natural question is under what kind of conditions the fibrations admit moduli spaces? Again, this is a very subtle problem. And then you can ask, how do they look topologically? Even when X to Z is identity, you can, for example, ask what kind of local fundamental group you have. So you can be led to many interesting questions and problems. And another general question is there any mirror symmetry here in general for low Calabi-Yaus, or under what kind of conditions you can have mirror symmetry? So it is not just in the global Calabi-Yau case, but you have a low Calabi-Yau, which is not even globally, may not be projected, but relatively trivial. You can still ask this question. And then there is also arithmetic, how the geometry of low Calabi-Yau fibration is related to arithmetic when everything is defined not over the complex numbers, but over some number field. So there are so many questions here to be asked, and this covers a lot of interesting problems. But now I will go into a few different topics in a bit more detail. I will mention some known results and some conjectures. First, I start with boundedness and moduli. One of the results that was proved a couple of years ago is a result of myself, which says that, very roughly speaking, suppose that Z moves in a bounded family, or even you can take it to be fixed. For example, just take Z to be Pn or any fixed variety. And then you look at all the possible local Avial fibrations over this fixed base, or this base which moves in a bounded family. Now, if these local Avial fibrations are of Fano type, roughly speaking, means that a minus k is big. Then if you fix the dimension of x, and these R here is just basically fixing the type of Z, which means Z is bounded, and this epsilon is bounding the singularities on X. And then these results say that all these possible fibrations belong to a bounded family. So if you take Z to be just one single point, then this is just the statement of the so-called Alexeyev-Borisov Alexeyev-Borisov conjecture. But when you take Z to be positive dimensional, then you need to work a lot more to prove this kind of statement. This is quite interesting because, for example, if you take Z to be again fixed, and then if you take any vector bundle on Z, you can look at the projective space of this vector bundle, which is a Fano fibration over Z. Then you can try to, for example, classify this kind of fibrations or vector bundles using these fibrations, and these boundedness statements say something about this vector bundle. Now, very hard conjecture in this direction is it says that suppose that you have a rationally connected projective variety X with epsilon LC singularities, and such that minus K is nef. Then the conjecture says that this type of varieties of fixed dimension, they should be bounded. Now, in fact, this does not even directly fit into this picture of local Avial fibration, but it fits into a more general structure, which are called generalized local Avial fibrations. I don't know to define those things, but this will be naturally one of those kind of objects. You can ask all those questions that I mentioned about that type of more general local Avial fibrations. And so this is one of those conjectures. And this is known up to dimension 3, basically, a slightly weaker form, but in higher dimension is still quite open. Another conjecture due to Yau, as far as I know, says that if you fix the dimension, and if you look at all the smooth Calabi-Yau varieties X, which are strictly Calabi-Yau, this is not a common terminology, but just for this talk, strict Calabi-Yau means that the Calabi-Yau is simply connected. This canonical bundle is trivial, not numerically only, but linearly trivial. And also all the hi of OX, they vanish for I between more than 0 and less than the dimension. So in many contexts, people define this to be a Calabi-Yau, because in this talk, I consider Calabi-Yau to be much more general. So this conjecture says that in fixed dimension, all these type of Calabi-Yaus, dimension should be more than 2, they are bounded. Although this does not hold for dimension 2, interestingly, because in dimension 2, you have all the K3 surfaces, which are strictly Calabi-Yau, but they don't form a finite family, a bounded family. But it's expected that when you go to dimension 3 and higher, then you have this boundedness. So there is actually also an opposite conjecture of Miles Reed, I think, which says that exactly the opposite. These Calabi-Yaus should not be bounded. In any case, to prove or disprove this thing is very hard, and there are very, very few results in this direction. And one of the non-trivial results is a result of myself, Di Cerbo, and Svalti, which was just published last month on Archive, which says that this conjecture holds for Calabi-Yaus which are elliptic. So it means that they have an elliptic fibration over a base, and such that this fibration has a rational section. Rational section just means that you have a map from the base into the variety, which is generically a section. So this is probably the most non-trivial result in this direction so far. Now let's talk about moduli. In the case of abelian varieties, so first of all, we have moduli of varieties of general type, which is very well understood by now, even of pairs of general type. However, when you take a Calabi-Yau variety, there is no natural polarization. For varieties which they have ample canonical bundle, then you have a natural polarization, which is just the canonical bundle. But also on Fanos, you have minus k, but on Calabi-Yaus, there is nothing natural to take. So you have to add some ample divisor, and that's what polarization means, to polarize something. For abelian varieties, moduli was constructed by compact moduli, not just moduli of the abelian varieties, but you need to compactify it. It was discussed by many people like Statakian, Mumford, and then much more recently, Alexiev, who used basically ideas from the minimal model program to construct these moduli spaces. But much more recently, just this summer, I also showed that there is compact moduli space for polarized log Calabi-Yau and log Fano pairs. So basically this says that the moduli spaces exist with the polarization here is given by effective and ample divisors. And this result say that moduli spaces exist basically in the most general possible sense that you can hope for. And this is also similar to Alexiev. This is based on minimal model program together with moduli of stable pairs, with ample log canonical divisor. Okay, so that's enough for moduli, and then let's go to singularities and complements. So as I mentioned before, complement theory developed by Shakurov and Prokhorov studies elements of minus and k relatively over points on the base. Now, an n complement is basically a reformulation of the same thing, which says that this is of the form k plus delta, such that over this fixed point z, x delta is log canonical, and n times k plus delta is linearly trivial. So this just means that n times delta is in the system given by minus nk. So it just means a nice element of this linear system. So one of my results say that for Fano type fibrations, then n complements exist for n depending only on the dimension, not on the even on the singularities. The singularities you take KLT singularities. But there is a very hard conjecture of Shakurov, which says that if you look at Fano type epsilon log canonical fibrations, so let's just you take Fano fibrations x to z, where the singularities of x is bounded by some epsilon being positive, then this conjecture says that there are n complements which are KLT, which have good singularities for n depending only on n, on the dimension and on the epsilon, or the type of the singularities. And now this is proved out of dimension 2, but in dimension 3, this is wide open. In higher dimension, we know very little. In fact, I think this is one of the most difficult conjectures in algebraic geometry, and it's one of the most underrated conjectures, in the sense that not many people even have heard of this conjecture, but it's really something very fundamental. It says, basically, for all these type of Fano type fibrations, you can say something very non-trivial about their geometries. And this is really amazing, but it's just so hard that not many people even want to think about, unfortunately. Now, a related conjecture, again, of Shakurov says that if you have a local Avial fibration where the total pair here is epsilon log canonical, and you have, again, this Fano type property, then the base also should have bounded type of singularities. So I don't want to go into detail, but here on the base, you can also define some kind of boundary. And it says that Z together with this boundary must have delta low-canonical singularities for some delta, depending only on epsilon and on the dimension. Now, if we knew this first conjecture, then we also know that will imply the second conjecture. So both of them are still wide open and they are very complicated. In turn, all these conjectures are related to other conjectures and ultimately related to the termination of flips conjecture, which I mentioned some pages ago. So there are a lot of problems in this direction. Now let me talk about arithmetic geometry. So we go kind of beyond algebraic geometry. Although it's in a way still algebraic geometry, but traditionally called arithmetic geometry. Suppose that we have a variety x defined over any field k, then as the notation xk will denote the set of rational points on x, which are rational with respect to k. Now, Arnold proved that if x is a smooth Fano variety over k, which is a finite field, then xk is always non-empty. So in other words, you always have some rational point over k. This is a really nice result. In another direction, Graber, Harris, and Starr, they show that if x is any Fano variety, or even more generally, any rationally connected variety, and if k is the function field of a curve, then again, you always have a rational point. So for example, if you have over the complex numbers, if you have a Fano fibration over a curve, then the generic fiber will be one of these rationally connected varieties defined over the function field of that curve. Now, for abelian varieties, there is a famous theorem of Mordell and Weil, which says that the set of rational points over k, where k is a number field, is a finitely generated abelian group. So we know many nice results about arithmetic of Fanos and Calabi-Yaus, I mean, in special cases at least, but there are also a very hard problem in these directions. So one of these problems is the problem of Lang and also Campana in a more general form. But if I state it in a simple form, this says that if x is a smooth Fano variety, or if it is a smooth Calabi-Yau variety defined over a number field, then there is a finite extension of this base field such that after this finite base extension, we have many rational points. To be more precise, the set of rational points becomes dense. So in general, x may not even have any point over k. So that's why you have to extend your field. But the conjecture is that just after one finite extension, you have many rational points. So this is a very hard conjecture. But it is known in very low dimensions, like dimension 1 and 2, and also in dimension 3 in not in full generality, but I think for Fanos maybe it's already known, but not for Calabi-Yaus. But when you go to fibrations, Calabi-Yau and Fano fibrations, the situation becomes even harder in that case. So for example, just look at this conjecture. If x is a conic bundle over P2 defined over number field K, so conic bundle means that the general fibers are, they have genus 0. But they may not be isomorphic to P1. They are defined over this over some fields. Then there is a finite extension of the field K. As before, there is a finite extension such that after this finite extension, you have many rational points. In other words, the rational points become dense in the Zariski topology in X. So this is really, I mean, the statement is very, very simple. You just have a conic bundle over P2. This couldn't be simpler than that, but even this is not known. Okay, so we don't have too much time left, so I'm going to be a bit quicker here. I will talk about rationality and rigidity, and then mirror symmetry, and then I will finish. Now, suppose that we have we look at Fano varieties, then there is a very natural question: which Fano varieties are rational? Rational here means being birational to the projective space of the same dimension. So, for example, in dimension 1, we have only one Fano variety, which is P1, and obviously that's rational. In dimension 2, all Fano varieties, at least smooth one or with mild singularities, they are automatically also rational because they will contain many rational curves. But once you go to dimension 3, then the picture becomes much less clear. Or you can ask something a bit simpler. If you look at hypersurfaces in the projective space Pn, which smooth hypersurfaces are rational? Because here we want the degree of D to be less than or equal to n to get something which is fun. So these are very non-trivial questions. Now, a long time ago in the early 70s, Clemens and Griffith, they showed that X3, which is a hypersurface defined by degree 3 equation, this is not rational in P4, at least the general one. And remember also, I mentioned the result of Iskovsky and Manin, who showed that a quartic hypersurface of degree 4 in P4 is not rational. And I also told you that this played a major role in the development of birational geometry in dimension 3. And these techniques that were developed by Iskovsky and Manin, who were all in turn they borrowed from Fano and other people. This was developed by many more people like Poklikov, Chelsov, Corti, Deferne, Ein, Mustata, and so on. They finally showed that if you take xn inside Pn, then this is not rational. In fact, they show something even stronger. They show that this is birationally rigid, which roughly speaking means that it's not even birational to any other Fano variety. For example, in particular, it's not birational to Pn-1. Using different techniques, Kolar showed that a very general hypersurface of degree D in N is non-rational if D is more than or equal to this number, the round up of n plus 2 divided by 3, where n is more than or equal to 4. And then in this direction, Vazan, Kolio-Telen, Pirotka, and other people introduced new ideas using Chow groups of 0 cycles and so on. And Totario, combining these techniques, he showed that a very general hypersurface in Pn is not rational, it's something more stronger, even not stably rational, if the degree satisfies this inequality similar to Kolar's. But there we have n plus 2, we have here n plus 1. And Schreider improved these things by showing the same statement, but for D now here more than or equal to the log of n plus 2. So these are some results in this direction. And finally, let me say a few things about mirror symmetry, and I finish my talk. Mirror symmetry emerged from mathematical physics, from string theory, but it was formulated, at least in some cases, in terms of purely mathematics. Now, Batirov, he, inspired by all these mathematical and physical progress in this direction, he constructed mirrors in the following example. So this is at least easy to understand. If you take R3 and if you take a reflexive lattice polytope, so this is just a polytope where the vertices of the polytope are lattice points. So you take a lattice inside R3. It's reflexive. Means that when you look at the dual, so you define the dual in some sense, and then the dual of the dual will be P itself. and also some other conditions here, like the origin should be the interior of the polytope. So let's not go into much detail. So we have some kind of nice polytope sitting in R3. To that, we can associate a toric variety, and we can also associate another toric variety, YP dual, to the dual of this lattice polytope. Now, these are both toric Fano varieties. And the mirror symmetry basically here says that if you look at elements of the anticanonical system on YP, these elements are mirror to elements of the anticanonical system on the other Fano varieties defined by this dual polytope. In particular, this includes maybe one of the most famous examples of mirror symmetry for the quintic example. Quintic means that you look at a degree 5 hypersurface inside P4. And that fits into this example because you can make sure YP is the projective space P4, and then you can take this X to be the quintic. So that's an example. And then there are some conjectures in this direction of mirror symmetry. One of them is due to Strominger-Yau-Zaslow, which roughly speaking, it says that if you take any smooth Calabi-Yau X, then you expect to have a mirror Calabi-Yau X check dual, such that these are in some sense mirror, in the sense here, for example, that they both have special Lagrangian torus fibrations. The smooth fibers of these two fibrations over the same base, they are dual in the sense of being tori. And also there are some transformations from these fibers of F given to the fiber on the other side, which take geometric data on X to symplectic geometric data on the other side. Now there is a different version of mirror symmetry that is due to Conservative, called homological mirror symmetry. It says that if you take any smooth Calabi-Yau variety X, then you expect to find a mirror X check where the derived category of bounded coherent sheaves on X is isomorphic to some other category called Fukaya category, which is related to symplectic geometry of X check, and these two should be in some sense isomorphic, equivalent as categories. There are other topics to discuss, so I just opened the page, but I'm not going to talk about them, and I will stop here. And thank you for listening.
Okay, thank you very much. And there are some questions in the Q&A. Can you have a look? Okay, yeah, there are 4 questions.
The first one says, should symbols doesn't matter in the Calabi-Yau conjecture just stated. Probably for, let's say, okay, I mean, we cannot take log canonical, probably. That is, I don't think it's abounded, but for KLT singularities, I mean, the problem that could happen is like that. If you have some non-trivial singularities, and then you, if you extract a divisor with bad singularity, then potentially you could end up with a fibration over, let's say, for example, in the threefold case, if you end up with a fibration over K3 surfaces, then in that case, we know that the base is not bounded. So that could be potentially a problem. But I think there should be a way to formulate the conjecture also for non-smooth one. I mean, one formulation that I know is that if you take the Calabi-Yau to be rationally connected, which necessarily will be singular, then this in fact is related to another, it's a special case of the conjecture of McKinnon and Prohor, which says that if the singularity type are good, which in this case, in fact, is automatically the singularity type will be bounded, then that conjecture says that this type of Calabials should be bounded. So at least in the rationally connected case, the conjecture should be true or expected to be true. Okay, let's go to the second question. It says that, well, this is a set of questions. First one is said that, is there any relation between flips and decidability problems for groups, diamond lemma, and similar combinatorial things? Well, I can't really answer this question because I don't know what like decidability problems and diamond lemma are. At least if I knew that, I could maybe give you an answer. But let's go to the second question. Say, is there a topological counterpart for the conjecture about Neff and Calabi-Yau, something of the 10 and other form? If something is spannable by something with singularities, then it is smoothable by something good. Yeah, I must say that I don't know. I mean, partially because the question is not very precise. I don't know exactly what it means. Something spannable by something with singularity. Does that mean you have sections that you move your divisor to something else with some singularities? Does it say that if you have a section, then you can take maybe something which has no singularity? I don't really know. Question 3, is there any diamond lemma for Fano fibrations and positivity? Again, unfortunately, I don't know what is diamond lemma, so hopefully, well, there is also a fourth question. Can flips and birational equivalences for varieties be organized into groups with explicit generators? I don't really know. I mean, how do you make connections between flips and groups in the first place? Flips are related to algebras, to graded algebras in a natural way, because they, as I stated, their existence is equivalent to this finite generation. But how do you relate these to groups? I don't really know. Okay, let me go to the next question. Say that regarding Shokourov's epsilon delta conjecture on Fano vibration, is it expected that delta only depends on the relative dimension and epsilon, not dimension of x and epsilon? That probably is true, because you can always take hyperplane sections on the base after taking some resolution or extracting some divisor. You can take hyperplane sections and reduce to a lower dimensional case. So the most difficult case is when the base is one dimensional. So the answer should be yes. So what matters here is the relative dimension and epsilon. Next question, can local Avial be formulated in terms of dx, such as Calabi-Yau categories? Well, there is an expectation for the log case. I mean, in the case of, for example, if you have a Fano fibration, then the derived categories, for example, if you have a flip or divisorial contraction, the derived category on the top space usually gets smaller when you go to the second space on the base. In fact, this is closely related to the minimal model program. So in each step, it's like you chop away some part of your derived category. But in the Calabi-Yau case, for example, in the flop case, then derived categories are expected not to change. Basically, if you have two varieties which birationally have the same canonical divisor, then the derived categories should be the same. So it depends. I mean, you could have, if you have a local Avial, just in the flipping situation, you have x to z. I mean, x could be ample over z, but after adding some boundaries, it becomes numerically trivial on the base. So in general, I don't know how to formulate this in terms of derived categories, especially having these divisors. Okay, finally, there is a question: curve bounds and immersed disk, curve bounds and embedded disk. So what is the question? Seems to be just a remark. Okay, I think I went through all the questions. If there is any other question,
thank you.
we can go through.
Yeah. So are there any more questions? There's someone raise hand. Let me see. Oh, no. Okay. I think that's all.
That was a great talk, Caucher.
Thank you. Yeah,
Thank you.
maybe I covered too many things.
No, it's beautiful. Very good. Thank you.
Okay. Thank you. So see you in December. Yeah.
Okay, see
Okay.
you next month, where we will have a workshop on moduli spaces. So there will be several talks. Moduli varieties.
Okay.
Good. Very much.
Okay, see you
Okay.
next month.
Okay,
Bye.
see you.
Bye.